Global LNG demand is increasing rapidly because natural gas is considered to be the cleanest burning fossil fuel. Other features of LNG include low carbon dioxide, CO2, emissions, ease of transport, sustainable development, and energy security. Different types of natural gas liquefaction plants have been developed globally to meet rising demand for LNG. The selection of LNG technology involves parameters such as equipment, like compressors, turbines, heat exchangers, etc., and process definitions, like pressure levels, temperature range, type of refrigerant, etc. However, LNG technologies are cost-intensive, as they require a large amount of energy for the processes of compression and refrigeration. Therefore, further developments are required to save costs and improve the efficiency of existing gas liquefaction processes. Here, a preview is given of aspects related to the theory of the technology and the parametric study of LNG plants and their development. Existing and future traits of processes are analyzed in view of recently constructed plants. LNG gaining ground as gas demand source. Energy plays a prominent role in the quality of human life, in terms of both manufacturing and services. Natural gas is becoming a dominant source of energy in several countries around the world. The transportation of natural gas has been carried out safely and economically via pipeline for almost a decade. However, in the 21st century, it has become clear that the majority of new gas reserves are difficult to locate. The latest developments in gas exploration and extraction have been aimed at stranded reservoirs that were considered too distant, costly, or challenging to develop in the past. Among the different solutions for exploiting stranded gas reserves, gas liquefaction has helped bring large, remote gas fields to market over the past few decades. These distant gas fields are often unreachable by pipeline. Long-distance transportation of LNG is possible by ship and truck due to the physical properties of gas in its liquid form. LNG can also be stored in places where geological circumstances are not appropriate for developing underground storage service. However, the costs of building an LNG production terminal are higher compared to other energy projects due to a number of factors, including safety considerations, remote construction areas, stringent design specifications, and large quantities of cryogenic material. Developments in LNG technology have reduced project costs in recent years. Emissions of air pollutants from the direct combustion of oil and coal are significantly higher compared to that of natural gas. The LNG industry becomes competitive to gas pipelines and other transport alternatives because it offers flexibility, attractive economics, and security of supply. The composition of LNG depends on the source of the feedstock gas. LNG composition includes methane and other higher hydrocarbons, sulfur, nitrogen, and carbon dioxide. The typical compositions of LNG from different countries are listed, and LNG is a clean source of energy because its combustion products contain trace amounts of nitrogen oxides and almost no sulfur oxides. LNG has standards, codes, and regulations that ensure excellent safety and security. Many complex and expensive LNG energy projects are underway around the world. The LNG value chain consists of a set of unique values. For each component in the LNG value chain, the percentages of average capital costs are shown in. A major portion of the cost is occupied by the liquefaction plant, accounting for almost 41% of the total cost. All other components comprise smaller, but still substantial, cost amounts. The production capacity of many LNG plants in operation or under construction surpasses 6 mtpy of LNG. Several developments have been made in the LNG industry to reduce energy consumption. Let's discuss about LNG process and technology after introduction to LNG process. A simplified LNG schematic, including process units and utilities, is shown in forthcoming slide. Liquefaction technologies are classified on the basis of refrigeration cycles, for example, open cycle processes and closed cycle processes, as shown next. In an open cycle process, the refrigerant may be part of the natural gas feed. In the closed cycle process, the fluid refrigerant is separately supplied and recirculated through the liquefier or heat exchanger. The refrigerant feed can be single or mixed. Gas liquefaction processes are differentiated mainly by the type of refrigeration cycle employed. Here, the most common onshore gas liquefaction technologies that have been successfully operated in land-based liquefaction plants are discussed. A brief description of these technologies is outlined in. Let's discuss about propane pre-cooled mixed refrigerant process, C3MR. The C3 mixed refrigerant process involves a pre-cooling cycle that uses a single-component refrigerant, propane, and a liquefaction subcooling cycle operated with a mixed refrigerant. A process flow diagram is shown forth. During a pre-cooling stage, the refrigeration cycle is applied in multi-stages at different pressures to cool both the gas stream and the warm MR to approximately -35 degrees Celsius. The fluid circulation continues with a multi-stage compressor, which compresses the vapor propane from a different pressure level to a constant outlet pressure. The heat exchange continues until the propane stream becomes liquid in the condenser. After condensation, the propane stream is throttled many times throughout the pre-cooling heat exchanger networks to vaporize it again. In the liquefaction subcooling cycle, the temperature of the natural gas is further reduced from -35 degrees Celsius to approximately -160 degrees Celsius. A flash separator separates the partially condensed MR during the pre-cooling cycle into vapor and liquid. Both streams are passed through the main cryogenic heat exchanger. The liquid stream is removed in the first section and recirculated through the shell side, while the gas stream goes all the way through both sections/bundles. It is throttled at the top and recirculated on the shell side in the same way. Prior to the compression process, both streams are mixed again and then vaporized. The compression is carried out with a 2 or a 3 compressor arrangement, followed by intercooling. In the MFC process, 3 mixed refrigerants are used to execute the pre-cooling, liquefaction, and subcooling steps. A multi-stream heat exchanger arrangement is used for the 3 cycles. In the pre-cooling cycle, the natural gas stream, liquefaction, and subcooling refrigerant are cooled to approximately -50 degrees Celsius. Both the natural gas stream and the subcooling stage mixed refrigerant are cooled during the liquefaction cycle. A typical MFC process flow diagram is shown in the slide. Pre-cooling is carried out in a plate fin heat exchanger, PFHE, by the first mixed refrigerant, and the liquefaction and subcooling are carried out in a spiral wound heat exchanger, SWHE, by the other 2 refrigerants. In both heat exchangers, the pre-cooling mixed refrigerant vaporizes and is used to cool the warm side streams. The vaporized streams are compressed for liquefaction in the pre-cooling condenser. The pre-cooling process is followed by the liquefaction process, where the liquefaction mixed refrigerant is further cooled by throttling on the cold side. The cooled stream vaporizes when used as a cold side in the liquefaction heat exchanger, and the warm side streams are cooled. The vaporized, cooled refrigerant is then compressed for liquefaction and cooled by the liquefaction cooler. The liquefaction mixed refrigerant recycles in the pre-cooling heat exchanger. The cooling mixed refrigerant enters the subcooling heat exchanger after passing through the pre-cooling and liquefaction stages. As in the previous stages, the throttled side vaporizes and the warm side streams cool down. The refrigerant is sent to the subcooling compressor, where it is again compressed, cooled via subcooling, and sent back to the pre-cooling and liquefaction process. All cycles require more than 1 compressor and intercooler. The optimized cascade process, OCP, is a simple and reliable technology. A process flow diagram for the OCP is shown here. In this process, 3 pure component refrigerants, namely propane, ethane, and methane, are used at different pressures during the refrigeration and liquefaction processes. Centrifugal compressors are used for the circulation of these refrigerants and cooled within a series of brazed aluminum vertical cold boxes. The power is supplied through frame 5 gas turbines. For both the pre-cooling cycle and the Mr. cycle, 2 gas turbine drivers, 30 megawatts frame 5, are normally used. Each train contains 2 compressors that operate at 50% capacity to achieve low operating cost and high plant availability. The dual mixed refrigerant DMR process has been used for train capacities averaging 4.8 mtpy. The process configuration is similar to the propane pre-cooled mixed refrigerant process, with pre-cooling requiring a mixture of ethane and propane rather than pure propane. SWHEs are used for pre-cooling. Frame 7 gas turbines are responsible for driving the refrigerant and axial compressors. For compression of cold refrigerant, axial compressors are used during the compression stages. The DMR process uses parallel compressor trains for each process stream and can be operated with both PFHEs and SWHEs. A process flow diagram for a DMR process is shown here. This technology is useful for large-scale capacities of 5 MNTPY, 8 MNTPY. Thank you for watching this video. Do like and subscribe this channel. Please stay tuned for more upcoming LNG videos.